okay, yeah, so yes, so now we start the first talk today. Yeah, sorry, okay, yes. The first speaker today is so Aaron Chan from Nagoya University. So the title of his talk is Categorification of Curves and Quasi-Triangulations on Unpunctured Non-Orientable Marked Surfaces. So please start.
Right. Thank you very much for the introduction, and let me also first thank the organizer for inviting me to speak here. Right. Yeah, the notes of this talk is already in the chat box if you have not noticed yet. Right. So this is joint work with Leslie, Matt, and Wright about non-orientable surfaces. But soon you will know that I care more about an orientable one rather than the non-orientable one. But anyway, so let's get started. So let me start with an overview of what I'm going to talk about. And the overview is just to first remind, well, roughly what happens in the classical case. And when I mean the classical case, I mean the orientable case. In a non-orientable case, you kind of care about marked orientable surface. And then if you have a triangulation on them, then you will get something called Jacobian algebra. And this Jacobian algebra is actually a gentle algebra. But maybe I should also say this is a gentle QP, whatever this means. And since you have a QP equivalent potential, then you can get a Army's cluster category. In short, I would just say cluster category. Yeah, so roughly these two things are I consider as the same. Yeah, and this is kind of the first thing one want to do. Then next I will we like to consider curves. So things like this thing which goes around the torus, and they correspond to certain intercomposable objects. So maybe I should say families of intercomposable objects. Yeah. In the cluster category. And then you kind of want to use this information to get a categorification of the triangulations. And this is done by something called cluster-tuting category. Sorry, cluster-tuting objects, yeah. Subcategories also works, but anyway. Right, yeah, so a triangulation is something that looks like this bunch of colored curves. It cuts your surface into triangles, right? Yeah, so this is pretty much, these two correspondences are goal 2 and 3. And the ultimate goal is to do something more, which is to categorify also the mutation, or in the language of surface combinatorics, they are the flip of triangulations. And you also want to do it in a way that is compatible with like cluster variable or Tekelmans theory, whatever setting you want. Anyway, so kind of the natural question is, so everything I said here is about orientable surfaces, and so you can ask, so what about non-orientable surfaces? And the idea of doing this is, well, orientable surface, or actually, regardless of whether it is orientable or non-orientable, you can always find a two-sheeted cover or a double cover, which I denote something like this here, and take an orientation reversing automorphism, which is of order 2, then you will get your starting surface. And I'll use this idea to kind of do the first 3. Right, so let me get more precise about what all this means. Right. So the setup, whenever I say surface, I mean a compact 2-dimensional manifold which has non-anti-boundary, and I always equip it with some finite set of mark points, and all these mark points are always on the boundary of the surface, so it is unpunctured surface. And a typical example would be something that looks like this. The map points are these two. Yeah, there's some small cases that you ignore, but let me not talk about that. And yeah, eventually the topology will not be so important in this talk, but in case you don't know what non-orientable surface is like, then I'll give some examples, and the examples are, well, the building blocks of the non-orientable surface, which is the projective plane. I imported this cute animation from YouTube that you can find if you search the cross-cap about how you can construct the cross-cap from a disk. Yeah, so actually whenever I say cross-cap, I actually means taking out a disk from projective plane. And so this is what it looks like in real life, but topologists have a way to draw them in more simple terms, which is to just draw a symbol to signify that you have the projective plane connected to your surface. So a Mobius strip will be drawn like this, and a time bottle, and if you take out a disk, and then they will be drawn like this, so on and so forth. Yeah, so these are just basic, and I'm not going to talk so much about the topology, and maybe refer you to Veronique's talk she has done in Cambridge in Isaac Newton Institute last month that you can find on the cluster algebra program website. Yeah, right. So the more important thing, as I said, is the double cover. That this is the thing that I care more about than the actual non-orientable surface. So if you have mounted non-orientable surface, it can be orientable, but everything is quite trivial there. Then you can find the two-sheeted orientable cover, and also an orientation reversing automorphism of order 2, so that this thing is the same as well doing this quotient. So in picture, then, well, a Mobius strip which I drawn like this, then you can find a double cover, which is just a cylinder or an annulus. And yeah, so this is the first sheet, and this is the second copy of the thing. And yeah, and this is usually how I think about non-orientable surfaces. I just think about the orientable double cover as a whole and just look at like a single region of it as the non-orientable part. Right. As I said, I want to categorify curves and triangulations. So what are they? Like I want to be specific about what I mean by curves. So whenever I say a curve from now on, then it either means a closed curve or a non-closed curve. A closed curve is something that is has no distinguished endpoint. It's just a loop or circle, and of course I assume it is non-contractible, and I also assume it does not intersect the boundary, so non-contractible, and so the intersection of the boundary is nothing. And by non-closed curves, I really mean closed with two distinguished endpoints, like these two, and yeah. So these two distinguished endpoints, they both lies in the set of mark points, and of course in the interior, then you have no intersection with the boundary as well. Right. And as usual, I always consider my curves up to isotopies that fixes the boundary component pointwise. Right. So the main notion of the talk is about non-crossing property. And by non-crossing, I will always mean that so there's no intersections. between the curves with itself or curves with another curves, then I can allow intersection at the mark point, so at the end points, right? And the main player, so not all curves are created equal, but the one that we really care about are the ones that are non-crossing. And in the classical orientable case, you care more about the non-closure curve for some reason. Okay. Curve. And actually, the boundary curve are not so important. So we usually just look at internal arc. So these are the one that does not look like a boundary component, a boundary interval, sorry. So now I need to talk about something that does not happen in the orientable case, which are some special behavior of closed curves. There are two types of closed curves in a non-orientable surface. So a one-sided closed curve is one that is non-orientable. And the other class is the two-sided closed curves, which are the non-one-sided closed curves. If they are simple, then you can, there might be a more helpful way to think about this definition, which is if it is simple, then this definition is equivalent to having a regular neighborhood, which is homeomorphic to the Mobius strip. And you can guess what is the equivalent case in the for the two-sided curves, which is the exister regular neighborhood, which is homeomorphic to an NLS. So let me just demonstrate very simply in the case of a Mobius strip. There's only one-sided closed curve, which is on this cross-cap picture, it will be drawn something like this. And if you want to draw it on double cover, then it looks like this. Yeah. So on the usual picture you see in any math book, then this curve here. It is also called a core of the Mobius strip. Yeah. And the two-sided closed curve on this surface will be the one that you see usually, which is this one. This is two-sided. And if you draw it on the double cover, then it becomes two copies of the same thing. Yeah. Yeah. So this will come back to us. That's the key point. So one-sided curves is just one curve on the double cover, and two-sided curves has two copies on the double cover. Yeah. And for simplicity, people invented the term quasi-arc, and this means that either a one-sided simple closed curve, I can't spell, or just an ordinary arc. And by simple, I mean, so this is no intersection, no self-intersection. You probably know what is a triangulation, so let me just write down the definition as well. The triangulation is just a maximal collection of pairwise non-crossing arcs. So we can generalize this to say, well, a quasi-triangulation will be just a maximal collection of non-crossing quasi-arcs. Right. So in the cross-cut picture, kind of the non-trivial example of quasi-triangulations are shown below here. There are 6 of them if you have 2 mark points on your surface, on your boundary. And 4 of them, they are honest triangulation, and these 2 are quasi-triangulations that are not triangulations. And so you can see the one-sided simple closed curve appearing here. Yeah, so there are geometric reasons why they choose this convention. So instead of like two-sided closed curve, This comes from Takamura theory, which I will not talk about, right? Right, so this is pretty much all the topology that I want to talk about. Next, I will go to the algebra. So I will start by reviewing the orientable case. And for the orientable case, I'll use I will fix this notation for orientable surfaces. And this is the triangulation on an orientable surface. When you have such a thing, then you will get something called quiver with potential, which is a quiver with some linear combination of cycles. And your quiver have vertices coming from the internal arcs of your starting triangulation. And the arrows comes from the angles inside the internal triangles, of your triangulation. And the direction of the arrows comes from clockwise orienting the angles. And the potential is given by, well, summing up the length 3 paths, one for each internal triangle. You just choose any one of them. And from this QP, you can get something called Jacobian algebra, which is the path algebra quotient out by the cyclic derivative of the arrows. So in this specific case, then I can actually just rewrite this as so all the length 2 path in an internal triangle, right? And you might complain about whether I should complete or not, but actually in this particular case, which is unpunctured surfaces, then the Jacobian algebra arising is actually finite dimensional, and in fact it is also a gentle algebra. I will not talk about what is a gentle algebra, but kind of take this as a definition. Yeah, these are not all the gentle algebra, but only part of them. But I will refer you to the next talk if you want to know more about gentle algebra. So for simplicity, I will call all the QP arising in this way a gentle QP. And an example, which is an hexagon surface with the triangulation where the internal arcs are labeled by blue, then I will have 3 angles in my internal triangle. So this gives me the arrows in my quiver where I will orient everything clockwise around the corresponding mark point. So if I draw this again here, then I'll get this quiver here. Then I'll just need to pick length 3 path in my internal triangle. I can pick any of them, so I just pick A, B, C, and then the Jacobian algebra will be just this bounded path algebra. Right. So I guess Yan's background has more example of triangulation of a hexagon that you can look about. Right, but the result that I really want to recall is by these people, name too long, I will not pronounce, where they show that, well, triangulated orientable surface, so orientable surface with triangulation, they correspond to gentle quiver potential, right? So we can do the same thing for non-orientable surface as well if we just remember that, well, there's an orientable double cover and then a specific orientation reversing automorphism of order 2 on this double cover. If you translate all the thing to the combinatorial world, then what you get is a quiver with an involution. And in the language of Dux and Raymond, they call this a symmetric quiver. Here, involution is a permutation of the vertices and the permutation of the arrows, which is of order 2, and it swaps the direction of the arrow. So yeah, so this really corresponds to the orientation reversing property of this homeomorphism. And then Right, and if you want to think more algebraically rather than combinatorially, then you can say you're specifying such a thing is kind of equivalent, not really. Is kind of the same as saying I have isomorphism between the path algebra and the opposite of the path algebra, right? So I can extend this notion to QP as well by saying that an involution on a QP, so an involution on Q such that it fixes the potential, right? So some example of what these the things look like. The basic case is the A2 quiver. Then you can have an involution that swaps the two vertices, but leave the arrow fixed. In general, any AN quiver linear oriented can equip with a non-trivial involution on it. And more non-trivial case is the Kronecker quiver. Again, I can swap the two arrows and I can still leave the two arrow fixed. It is still an involution, but this kind of involution is not the one that I am interested in. I'm interested in the one which has a specific property. And you can find out this specific property if you just think about what happens on the surface. So if you just think about this setup, then you will realize that this induces an involution sigma on the QP QW such that it is fixed point free. And this is the really crucial property that allows many things I wanted to work fixed point free. And henceforth, I'll probably abbreviate this as FPF. And I mean fixed point free on both vertices. Yeah, oops, yeah. On both vertices of the quiver and the arrows, so. Right, so here in the above example box, I have shown an example of how this came about. So this is the easiest case of non-orientable surface, or really the double cover of the non-orientable surface, which is the cylinder with two arcs, and you know this is the Kronecker quiver, and this is the double cover of the basic case, the easiest case of an triangulation on a non-orientable surface. And in general, if you want to do this exercise, you can look at the A and N quiver. Yeah, this has an involution, and this corresponds to kind of the fan triangulation of the Mobius strip. So this is the first thing we did, which is to extend the previous correspondence between triangulations and gentle QP, and then just say that if you have a non-orientable surface and say this is connected with a triangulation, then you can find a connected quiver with potential which is gentle, and it comes with a fixed point free involution. And of course, I'm not. Many of you know I'm not a cluster theorist, and I really care more about gentle quivers or locally gentle quivers, and so there's no special thing about cluster theory in this proposition. It really works for locally gentle quivers as well if you push your setup to that setting, and also the orbital surface and so on and so forth. Yeah. So anyway, I'm a bit late than I hope. Yeah. So next, let me review the classical correspondence between objects in the cluster category and orientable surface. From now on, I'll fix my underlying field as complex numbers, because ultimately you want to do some Grassmannian thing. So but if you only care about the algebra, then you will at least need a field whose characteristic is not 2. anyway, so the classical case as a dictionary between topology and category. As I said in the beginning, if you have an orientable surface, then you get a cluster category. So this is a specific kind of Grisham finite to COI triangulated categories. This category have some special property, namely that if you consider all the non-closed curves, then they correspond to a certain type of indecomposable objects, which I would call string objects. And then there another class of indecomposable object called the band objects. They correspond to closed curves equipped with some non-zero scalar. And so in practice, I will write an element in here in this form, which is by a primitive closed curve. And by that, I really means, I will keep writing this. That a closed curve which cannot be written as a power of some kind of shorter closed curve. And so these string objects and band objects, they contribute to the whole family of decomposable objects inside the cluster category. And this is not the end of the story. As I told you, there's a correspondence between triangulations and cluster tilting object. So this comes from this property that the crossings between curves, they corresponds to a set of canonical bases of the X1 space. So what I mean by X1, the extension space of the cluster category, it means the home of the two things, but with the later one shifted by one. So since crossing corresponds to elements, non-trivial elements in the extension group, so arc, meaning that self non-crossing curves, they correspond to what representation theories call rigid objects. So they are just objects which have no self-extension. So X1 is 0. So these are crossing between any curves, not just one curve. So you can also combine these two to get a correspondence between triangulation and what is called a cluster tilting object. So yesterday in Peter Jorgensen's talk, you have seen a definition of cluster tilting object, but I will not use that definition because my category is thankfully to Calabi-Yau, so I can use this more convenient definition, which is a maximal rigid object. And if you think about the meaning of the topology, this is like really the same. Triangulation is a maximal collection of pairwise non-crossing arcs. So so this becomes a maximal rigid object. And when I say maximal, I mean if you throw in any more things such that the whole thing is still rigid, then the new thing that you throw in is already appeared in the original thing. So this means this is the maximality here. So this is the definition I'll use to do things later. The whole point of saying about this is that crossings corresponds to non-split extension. This will come back to us later. And then using this, so we want to think about, okay, how we work with the non-orientable case. Well, we have this distinguished involution on the gentle QP. So we want to make use of it categorically. Well, if you think about how this works in general, then you can easily come up with a functor, and this is an exact contravariant functor, and this is a duality functor, meaning that it squares to an identity functor. But I have to stress very carefully that this is contravariant, so it reverses the direction of morphisms, and it also, it anti-commutes with the shift in the cluster category. Right, and so this duality functor does what you want it to do, which is categorically it swaps a curve with the other copies in the other in the other sheet of your double cover. So if you have a non-closed curve, then you take the involuted partner of your curve, then you get precisely just applying this functor on this curve as an object in the cluster category. And likewise, if you have this decorated closed curve, then you apply this involution, and then applying this functor on such an object, then you will get the involuted, the partner curves, but with the decoration reciprocated. You need to take the reciprocal of your non-zero scalar, right? So to display the effect of applying this contravariant duality, so let me just do this Kronecker example that I showed you about. So the effect of applying this exact contravariant duality is that you send objects kind of around a focal point. You send this thing to this thing, and then this thing to this thing, so on and so forth. And on the homogeneous tube, which are the part where it consists of all the band objects, then it just swaps the component around, because, well, all it does is taking the partner curve and then take the reciprocal of the decoration, right? So with this in mind, then you can pretty much expect what we want to say, that how we are going to achieve the categorification of curves on non-orientable surface. So if you have a non-closed curve on a non-orientable surface, then you can lift it to the orientable double cover, and then they will correspond to a pair of string objects in the cluster category. So it's just this thing. And this also induces a triangulation formulation, namely triangulation, correspondence between triangulations and cluster tilting object. So triangulation on the non-orientable surface, well, you lift it again to a triangulation on the double cover, and then you take the corresponding cluster tilting object. So this cluster tilting object has a special property that if you apply the duality functor, then you get back to itself. And this is called the self-dual property, right? There's some story about mutation that I'll not talk about for time constraint. So the very basic case, which is kind of so trivial, is the Kronecker case. There is only one triangulation on the Mobius strip with one mark point, and it just corresponds to the initial cluster tilting object, right? So what about quasi-triangulations? Well, yeah, if you know about laminations or how they correspond to the decorated representations, then you can still formulate it in that term, but I kind of do not like that formulation, at least in this particular setting. It is a bit weird to have something non-rigid appearing. So I looked up, and another thing that I do not like in this kind of pre-theorem is that, so this is one, every one closed curve in here, it corresponds to a pair of indecomposable objects. So this is a bit not so nice, not so perfect, let's say. So I really want to work with the orbit under this duality functor. So after searching through the internet, I realized that we are very lucky because there is very, very recent studies about these kind of things. And this is our first, it seems this is first study in the paper by Dirksen and Wayman. They call it symmetric representation, but what this means is two different classes of representations. So one is orthogonal representations, and the other one, they call them symplectic representations. In a more compact way to denote this theory, I will follow the convention of Bruce and Torelli that they call this epsilon representation, where epsilon is +1 or -1, and +1 is the orthogonal case and -1 is the symplectic case. Right. So this thing, they are about representations of an algebra. So let me fix my setting I will use an algebra given by equivalence and relations, or a basic algebra, and I need to equip it with involution. This involution is an involution on Q, and it fixes the ideal. So this setting is the same as the QP setting. The QP setting is a specific case of this setting. So yeah, and yeah, as usual, whenever I work with modules, I work with right modules. Yeah. So yeah. So what are the symmetric representations? At the end, the definition may be not very enlightening, but yeah, since we are algebraists, so let me go through the definition. So for simplicity, I would say an epsilon form. This will be either a symmetric bilinear form or a skew symmetric bilinear form, and which one you take depending on which epsilon you take. Okay, and by an epsilon representation on a ring with involution, I mean an ordinary representation equipped with a non-degenerate epsilon form. And you want this epsilon form to kind of gives you the property that taking the partner arrow corresponds to taking the adjoint of the action matrix. So to write this out more properly, do I have time? No. So yeah, so this is pretty much what it says. First thing, yeah. First property is, well, you want your, if you look at this as a matrix, then you want your matrix to be 0 on everywhere else apart from when you are identifying one vertex with the involution of this vertex. And the second property is to say that, well, if you applied one action here, then the involuted action is corresponds to the adjoint of your original thing. And so, as I said, these are what gives you kind of the orbit construction for under the contravariant duality functor. Indeed, if you have an epsilon representation, then you can find, and there will be an isomorphism such that between this epsilon representation and if you apply the duality functor on it. Yeah, and yeah, there's also the property of detecting which epsilon you are working with. So you can just apply this and get that epsilon scalar coming up. Yeah, so I want to have a correspondence between some intercomposable objects with a single curve on the non-orientable surface. So I need a notion of intercomposability, and fortunately they are already studied. Yeah, so what I'm going to say can be quite technical, but you should just remember the slogan that an epsilon representation is really just playing with the anti-version of representations over a screw group ring. So yeah, it's really just an anti-version of like orbit construction. So yeah, this classification of intercomposable representations are already studied by Dodson, Raymond, Booth, and Torelli. And yeah, so if you have an intercomposable epsilon representation, then you can always write it as in terms of intercomposable, a single, or well, up to involution. Yeah, you can always find an intercomposable A module such that there are only 3 cases. So the first case is kind of what you would expect, which is so M is just bar time plus its partner. In this case, M and its partner is not isomorphic as A module. And in this case, we call the epsilon representation split. Yeah, they were called type S in this literature, but yeah, anyway. So the second case and third case, they correspond to the case when, well, your intercomposable factor is self-dual. And so the first case, ramified, is just taking 2 copies of the same thing, but really, you're really applying this contravariant functor first and then take them together. And the other thing is, well, M is just this indecomposable A module itself. In the original paper, they were called type I, and I means indecomposable, but I don't like this because then you will talk about indecomposable epsilon representations. So using our inspiration from surface, I will call this one-sided. So you know, you can expect what they corresponds to. Right. So yeah, taking this technology, then we just look at, okay, what happens to Jacobian algebra? So what are epsilon representations over Jacobian algebra equipped with fixed point free involution? So they are the case, the non-orientable surface that we are interested in. And in this case, exactly one of the thing occurs. So as before, we have some split case. Well, all the non-closed curve will arise from the split case. Yeah, so here these are non-closed. And there are also some band thing appearing, which I don't care so much. And then the other important things are the one-sided simple closed curve. They will appear as one-sided thing as suggested by my modified notation terminology. Yeah. The annoying thing is, yeah, so there's the epsilon is a bit delicate. But anyway, so there's also some other thing that appears, but for us, since we want to ultimately categorify quasi-triangulation, so these two are really the one that we care about. So let me redraw the correspondence between topology and epsilon representations. Then if you have a one-sided closed curve, then you can rewrite this as a one-sided epsilon indecomposable object. Namely, you just take this same thing, yeah. Right, and well, every one-sided closed curve has a two-sided counterpart. So in this case, of course, this also happens. So these are the two-sided, sorry, ramified. In this terminology, ramified epsilon decomposable, which are but yeah, so for some specific lambda, which I'm not talking about. And but now I have the same curve, but now I take two copies. So if you remember what I said like in the beginning, two-sided curves, when you go to the double cover, then it gives you two copies. And yeah, this seems works as we wanted. Right, and of course, the last case is the kind of easier case, which is the string part just splits. So if you take a non-closed curve, then it corresponds to split epsilon indecomposable. Yeah. So with this kind of correspondence, I think we can it's fair to say that we pretty much have what we wanted to do as an analog of GoTo for the non-orientable case. So now we want to talk about quasi-triangulations. So if you remember triangulation, they correspond to cluster tilting object, which are maximal rigid object. So yeah, I want to have a similar formulation for quasi-triangulations. Right. So recall our setting. Yeah. So now we go back from Jacobian representations over Jacobian algebras to the cluster category. Then you might know that the cluster category, if you have a cluster tilting object, and in this case, I'll take the minus shift of the initial triangulation. This is a cluster tilting object, and then you have the home functor from C, which will induce an equivalence from this additive quotient to the module category of the Jacobian algebra. Yeah, using this, I will call an object in the cluster category and in the composable epsilon object. If I don't have time, so I will write this. Yeah. And yeah, so either if you restrict to the module, well, you get in the composable epsilon representation, or it corresponds to the dual pair in the initial triangulation. Yeah, so in this case, now I will have a canonical triangle in the not non-canonical choices of triangles in the cluster category, so that your indecomposable epsilon object can be written as an extension of two things which are dual to each other. And I will call this particular thing, this is important, and I will call this one not the later one, it's an epsilon factor. So factor kind of hint for it, kind of like a quotient of it. So in the Mobius strip with two mark point case, then I can decompose this one-sided curve using these two arc. This also has a canonical isomorphism as before. And then I defined epsilon object as just direct sum of indecomposable epsilon object. So next I need the notion of extension. So this is the most difficult part, and it takes a long time to come up with this. Yeah. And this is pretty much like a classical extension, but instead of really taking extension between the two epsilon objects, I just take extension from one object to only the epsilon factor of the other one. And I require this extension to satisfy this property. And if you think about this as being an orbit construction, then this is, then you, when you take an orbit construction, you get a greater category. And this is like saying that this extension is in a single degree. Yeah. So, and this property will give you a commutative diagram, which looks like this. So yeah, so this is the first extension I started with, and then you take the dual, which is this one, and then you can, because of this property, then you can draw this thing. So what the significance about this thing? Well, they are all triangles. So all the rows are triangles and all the columns are triangles. So yeah. And then I will get the new thing here. I will call this thing the epsilon extension of, yeah. I don't know which one by which one, so I will write x over y. Yeah. And yeah, I will call such an epsilon extension split if this new object, this epsilon extension, they just correspond, they are just direct sum of your original x and the two factor of the other guy. And I will just write this notation if all epsilon extension splits. And in this case, I will define indecomposable epsilon rigid object as indecomposable epsilon object such that all the extension splits. So this is really the classical case, but I just put an epsilon in front of every term. Unfortunately, I don't have the perfect formulation of epsilon rigid, so I'm using this tentative one, which is direct sum of indecomposable epsilon rigid object such that all the direct sum ones, they are pairwise x orthogonal, x1 orthogonal. So if you recall, then this corresponds to the non-crossing property on the surface. Yeah, but anyway, so I have an example of showing why the closed curve on the Kronecker quiver is an epsilon rigid object, but I guess I don't have time, so I skip this and just comes to the final conjecture slash theorem. I'm saying conjecture slash theorem because, well, I have this theorem written down a week ago, so it's not double checked yet. But yeah, I believe not everything should work fine. So yeah. So what we have is just indecomposable epsilon rigid object. They correspond to quasi-arcs of your non-orientable surface, and as such, kind of pretty much by definition of how we define epsilon rigid object in general, then the maximal epsilon rigid object corresponds to quasi-triangulation of the non-orientable surface. Okay, so I guess I will stop here. Thank you very much.
So thank you for